So I am Joël Betsoa from IRCAM, and this is Frédéric Hélin, and we will present this presentation will be with the two of us. So I will begin, and then in 10 minutes I will give the talk to Frédéric. And I'm really pleased to say that now we can forget about the question marks, and we are able to, maybe Frédéric is able to demonstrate that the Resner-Beans nonlinear propagations is an integrable system. So, where is the... So the nonlinear model for Resner-Beans is simply a model where each sections of a beam is supposed to be a rigid part and has a rigid motion, so it can be described by a rotation and a pulsation. So we can think about a Lie group that is behind this. So the idea is to follow the paper of Arnold at the end of the 70s, and he was able to make correspondence between the rigid body motions and some dynamics of fluid dynamics. And he's just showing that if we just exchange the group, the Euler equation for the rigid motion exactly the same for the gas for the group of diffeomorphism. But now the Resner-Bean is one of the simplest acoustical systems. We have seen a complex acoustical system, but this one is really simple. But if we consider just like this the propagation of wave, then we will have an ordinary differential equations. If we consider an infinite dimensional configuration space, I mean all the shapes, the possible shapes of the Resner-Beans, it's an infinite dimensional Lie groups, the group of diffeomorphisms. But if we take the multi-symplectic formulations, then we can consider a PDE, so a partial differential equations, with now a finite dimensional Lie group. And this is achieved by increasing the number of independent variables. From times, we now consider space and time. And we will obtain a partial differential equations. So you can think of the minimal surfaces where if you have only one independent variable, you will have some geodesic curves. Then in this situation, you will obtain an n-dimensional submanifold. Here, it's a two-dimensional manifold. So, inspired by the work of Magnus, but also by the Russian schools or mathematical physics, theoretical physics, there is a correspondence between the Resner models and the harmonic maps, non-linear Zeeman models or principal carrier models. So let's outline our presentations. I will speak about the Resner models in a few details, and then Frédéric will show that it's an integral. Yes? So, as I said, each section is described at each time t and each arc length ends by a rigid motions. So we can describe any positions at a certain times and a certain arc length s and t. We can describe the motion of the section by a global matrix which collect the rotation matrix and the displacement. And each matrix H is an element of the group, the special Euclidean groups, which is a combination of the rotations in R3 and translations, so a vector in R3. So we can compute the strain and the velocity by differentiating the element, the position h in, by s or t. And we can also translate this tangent vector to the tangent plane to the identity by the left. So we have two vectors in the Lie algebra corresponding to strains and velocities. And if you differentiate, if you do a differentiation of the first one by t and the second one by s, by eliminating the cross derivative, you will obtain the compatibility conditions, and we will see that it will correspond to the zero curvature conditions. And the adjoint operator is related to the fact that the group is a non-commutative group. So if we now try to apply the Hamilton principles, we have to compute a kinetic energy and a potential energy. So assuming that we are making a linear straight stress-strain relations with the help of a Hooke matrix C, then we can compute those things. And those matrices, the inertia matrix and the Hooke matrix, can be divided in rotational part and the translation part. So here, it's the inertia momentum due to rotation. This is the mass due to the inertia of translations, and you can have also parameter to describe the torsions, the flexions, etc. So applying the Hamilton principles, we have an actions, and we are looking for the stationary. And if we do these things, we obtain, instead of earlier Lagrange equation, because there is a Lie group in behind these things, we obtain an earlier Poincaré equations. And as you can see, if we forget about the adjoint terms, it looks like wave equations, and the nonlinearity is somewhere in those operated. The important thing is to mention that the nonlinearity depends on the Lie groups and not on the particular metrics or Lagrangian we use to describe the models. So here you have the expression for this group of the adjoint operators. We can do exactly the same thing on the left, and by taking the velocity or the strains by translations by multiplying those velocities by or strain by translation, but on the right. And in this situation, the equation of motion is transposed to it will lead to the conservation law. And we have also almost the same compatibility conditions, but with a sign exchange. Okay. So to summarize, we can have two formulations. Using a left formulation, we have the Euler-Poincaré equations with this compatibility equations, or we can make a right formulation, and we have the conservation law and the same, almost the same. And as you can see, there is opposite sign. So, no, it's your turn.
Thank you. Okay, so now I will make some extra assumptions. So the purpose is to show that the previous model presented by Joel is completely integrable, but we need to assume there are more hypotheses. I will come back at the end on the hypothesis, but let's go on the very simplified model. There is one simplification which consists in imagine that we have an infinite beam, infinite road. So this means that the S variable, which is abscissa along the beam, is infinite. But just so this makes sense if you look at a locally the behavior. Or okay, you can also you could have a ring. Then you may assume that you have a periodic space. And second assumption, which is stronger, and I will also come back, is that you assume that the hook and the inertia tensors are isotropic, which was not the case, but it's a strong simplification. I will come back later on. And so with this assumption, then the relationship between pi s and psi s simplifies strongly, thanks to the isotropy. And it turns out that pi s proportional to chi s, and the same for sigma. And then by normalization, you can, okay, for simplifying, just assume this constant. J and C are just constant scalars equal to 1. Okay, then the translation of the simplification of the previous equation, thanks to this hypothesis, is a system of two equations. The second equation recognizes the conservation law, which is also the consequence of Noether's theorem. And the first one is a structure equation. Now, I will start by translating these two equations into another language, introducing in one form, omega, which is defined on space-time. Okay, but space is just abscissa again along the beam, and with this coefficient chi s and epsilon. And then we can define also the star of omega, which is imaged by the Hodge operator. There is some Hodge operator acting on one form. This is one form. We just exchange ds and dt. And the first equation just look at the zero curvature equation. Just a familiar equation, the Moore-Cartan equation, or equation which says that omega can be interpreted as a connection one form, which has zero curvature. And then second equation is a conservation law, or Noether's theorem. Okay, now after 30 years of wonderful discovery about the neural system, which started in the 60s, and where many mathematicians and physicists participate, we have a kind of magical way to translate again this equation. So further translation is to look at the combination of omega and the Hodge dual, the sum and the difference. Then you see that there are still one forms, but one is some element in the Lie algebra, some function to the right, times dst, the time plus space, and the other is a difference. And this looks like as the right or left moving forms. And then the magical thing is just completely strange at the beginning, is that you introduce a lambda parameter just out of the blue, but it has a long history. It's called spectral parameter for historical reasons. And it's a complex parameter, and you consider this combination of this omega left and right, which is just here, which is a meromorphic independent on lambda, and it's still a function on s and t, because the coefficients are functions of s and t. You can also write it differently. You can introduce this light cone variables, eta and psi, and then you can introduce functions u and v, and which are combinations in such a way that the omega right is just u, this function times dxi, and left is just the same thing with eta. Okay, then you have this other way to write. Now the magical thing is the key point of the integral system is that the system of two equations which were here, the two equations here, can be encapsulated into one single equation, or one family of equation, which is this zero curvature condition, true for any lambda. So it's one equation, but in the same time it's an infinite family of equations, because lambda runs over the complex numbers. And then this equation is particularly useful and powerful because you can use it for integrating and building a map from R2 the space-time. You have to imagine that you have R2, which is space-time, and CP minus plus or minus 1, which is the space of complex parameter. But you can integrate for each lambda fixed, you can integrate this omega in a nonlinear way and get a map into the complexification of the group of Euclidean motions. And then, since the coefficients u and v were real, meaning that they were taking values into the real version of the Lie algebra, you have the reality condition. Okay, so the key is to exploit the psi lambda, which is depends on two parameters: lambda, logical parameter, complex spectral parameter, and space-time variables, which are implicit. And now there are actually many ways to use many different points of view to use this equation. Sometimes we may see that this relation is equivalent to a Lax equation, although it's not a Lax equation in the standard way, but it's more or less equivalent to Lax equation. So I will present here one way to exploit this existence of psi lambda. This psi lambda, whose existence is only due to the fact that our solution, our maps, is a solution of the dynamics equation. And then, okay, this is quite, okay, not intuitive at the first glance. And the game is a kind of strange operation. We will fix the space and time variables, psi and eta, or s and t. And you will play with lambda. And we do complex analysis with lambda. So what you do is that you okay, I will just represent the complex plane. I forget momentously the space and time, and just drawing the space of complex parameter, and there are two poles, -1 and +1, and two disks. The choice of disks is not that important, centered at each singularity. Remember that omega lambda is, I don't remember exactly the notation, is singular. I forget exactly the. Oh, yes, that's you. Okay. Get psi plus v dx. You remember you had that, and so you have the singularity at -1 and +1. And what you do is that, and then you get psi lambda by integrating that. Psi lambda, a priori, has a singular behavior here and here because of this. So you may have a Laurent development with singularities there, and it may be holomorphic everywhere else, even at infinity. At infinity, it converges to some constant. And then what you do is that you solve a Riemann-Leibniz problem, which is a decomposition. So you look, for instance, here, what you do is that you look at psi lambda here, the restriction of psi lambda here, still psi and eta, sorry, fixed. And you decompose psi lambda using as a product of something which can be extended inside the disk in a holomorphic way, and something which can be extended outside. So I put a left because left index. Okay, or maybe the left index is upstairs. So I do that here, and I do the same thing on the right hand side. Then I produce out of psi lambda something which is I, holomorphic inside, and O, holomorphic outside. Okay, then, okay, we skip the details. You play with the, okay, you consider the connection form of corresponding to O, which is outside this disk, for instance. And you do the same thing with the connection, the one form built out of O exterior of this disk, and you do the same computation, similar computation on left and right. And what the point is that this form can be expressed in two different ways, in the blue and the red one. In the blue one, you use the fact that how O can be extended outside, and in the red one, you use the extension inside. Okay, then I skip the details, but more or less by comparing the two, you get this way two expressions for O, because there is a relation thanks to the map side here, and by comparing these two expressions and using basically UV theorem, you deduce that, for instance, so for instance for U, okay, you use for U left, so which was one of the coefficients is equal to 0. And if you do a similar computations for V, which is a coefficient of d eta, so U was a coefficient of disk size, this is 0, and V here is not 0, but it has a single pole. So this is just looking at the behavior of each function inside and outside and using the Fourier theorem. Then at the end, what you get is that these coefficients are extremely simple. You have 0 here, and here you have a very simple form. Now, this was the work where psi and eta were frozen. Now, psi and eta play again and run again, and what you do is that you come back to the very definition of O, because you knew that this small o, this small o was something like that. Okay, there is dependence on lambda, and it was on the left. And you knew that from that relation, you deduce that also O satisfies some equation. But now you know a lot of information about O by the previous work. And this equation reduced to extremely simple relations. We say to you that, for instance, V, the coefficient of 1 over 1 plus lambda, depends only on eta, and something symmetric with you had with the coefficient of 1 over 1 minus lambda. And then, okay, this means that this is two maps are solution of a linear equation. And this is this equation. So you have done a non-linear, relatively complicated and infinite dimensional transformation, which is this interesting transformation, which transforms a non-linear equation into linear equations, which is just this equation. And here you just have the solution is just one solution of one variable and another of the other variable. Then you can do the reverse operation. I don't describe it, but it uses exactly the same ideas, but just in other sense. So you have a kind of dictionary between solutions of a linear problem and solutions of a non-linear problem. Now, this was okay. There are still questions. The question is that once you have discovered that, you have to use it for computing, for instance, soliton solutions and some particular solutions. But if you work still, you still have to work. Hope to produce explicit solutions. Then, in principle, we could produce all solutions, but the transformation is very complicated. But the hope is to be able to build a simple solution and to compare with other methods. And also, lastly, there is some hope to extend to non-isotropic problems and not assuming that the Hooke and inertia matrices are isotropic. I thank you.
Any questions?
I propose to postpone the question during the cocktail.
One question.
You are the boss, of course, but a short question. No. But my question is, but you have an initial formulation in a form of partial derivative systems. It is more interesting to transform it in a problem with exterior derivatives or to solve directly the partial derivative equations.
I mean, both methods are interesting, and there are actually more direct methods using numerical methods, which are non-linear but simpler. And also there was a work of Joël with Florian Boger, I think. Anyway, what is interesting is to produce out of this method algebraic and explicit solutions, and then to test numerical methods. That was our first purpose was to produce explicit solution and then to test numerical methods on these solutions, and then to check whether these numerical models are good or not. This is one, but certainly both methods are useful.